Hello? Now it's ready. So good morning. You are very welcome to the first session about novel forest bio-based products. We have the first communication with Bruno about hydrogel coated papers for added value products, the PETRICELL dry and GELA case studies. Welcome, Bruno. I will make a brief introduction to Bruno. Bruno is senior researcher on paper technology at Alma Science Collab. He has a PhD in natural science for Martin Luther University in Germany, and his main expertise ranges from synthetic organic chemistry to pulp and paper industry, developing projects in the topic of biorefinery, chemical modifications of forest-based materials, and smart application for bio-based products. So all in one for PETRICELL and GELA. Thank you, Bruno. The floor is
Paula,
yours.
For this introduction. So hello everyone. Like already mentioned, I'm going to present today two projects from Alma Science on hydrogel coated papers, the PETRICELL dry and GELA. But before that, I just want to mention that there was a lot of people involved in this work. Some of them are listed here, some of them are not, and I'd just like to thank them in advance because this was, let's say, a lot of work involved. A little bit about Alma Science. We are a very new company or research institute. We are a co-lab established in 2019. And basically, we try to develop solutions for our partners, our associates, on the fields of printed electronics, smart paper, and smart cellulose applications. So we have here four main research lines: Cellugel, Paperweight Digital, Sphinx ID, and Smart Pack Technologies. And today, both solutions that I'm going to discuss will be on the line of Cellugel, so which are cellulose-based hydrogels for applications in life science and materials. Okay, so although we are a very new entity, we already have some success stories to share. So last year we already filed for 4 provisional patents applications, 2 with industrial partners. We are also part of 4 PRR agendas, and we are part also of different competitive funding projects. But now for the more interesting part, I want to start talking about PETRICELL. This was one of the first projects that started in Alma Science in collaboration with 2 of our associates, RAIZ and Clara Saúde. And it came from the need that one of our partners had to develop a microbial growth media solution that had the same results as the gold standard, which is agar-plated Petri dishes, but without some of this disadvantage. Like I said, today the gold standard for microbial growth medias are agar-based medias. These are very widely available from industry to university. They all use this kind of media because they're highly versatile, and also they allow streaking, which means that we can use at different types of samples. It could be biological samples, liquids, surface, whatever you like to try. You just streak it on the plate, and you analyze the microbial growth in it. And usually they are low cost, so they're not very, very expensive, and with a basic infrastructure needed. But usually this low cost is because most of the work is transferred to the operator, which need to prepare these Petri dishes, and need to, let's say, keep it stored at low temperatures with a very low shelf life, which can bring many problems regarding stock management. So if you do not manage your stock very well, it's very easy to obtain stock losses of these of around 10%, let's say. And also this is a biological waste, so afterwards everything needs to be incinerated. So again, agar plates are very heavy, so this also adds to the cost. So what we thought about it was making a solution based on cellulose. So first, in order to replicate the ability that agar has to grow this microorganism, we thought about a hydrogel on the surface, on the top, where microorganisms would grow, and then a base paper below this hydrogel to serve as support and water retention factor. Additionally, with this, it will also be possible to have, to expand this technology, to have integrated antibiograms, for example, and in the future, we also hope to have Petri-based Petri dish. Directly to the hydrogel preparation, we identified, testing different formulations, we identified that there are 3 main components that we need to have to really replicate these agar plates. First is a binding agent. Here is where we use usually our cellulose derivative. And this will serve as the base for the microorganism growth and the base of the hydrogel. We also need a gelling agent. We know that agar is a very special one because you just heat it up and after you cool down, you already have this very thick gel structure. And so we tested different types of gums, pectin, sodium alginate, and select among them. And also a plasticizer which helps us give this nature feel during inoculation during the operator. For prepare the hydrogel is very simple. We just mix the components at the defined temperature. And this, let's say, is one of the resulting formulations. As you can see, hydrogels are very thick, so they have very high viscosities, which kind of limits the amount of solids which we can go with these solutions. But nevertheless, we could move on to the, let's say, addition of the hydrogel to our fibrous layer, to our paper. And we use mainly 3 methods: bar coating, wet lamination, and drop casting. I will talk a little bit about that later. So by using these methods, we are able to also deposit this hydrogel in larger areas, so A4 sheets, or in some cases even a little bit bigger. Here in this picture, you can see some of that. And then we have the remaining steps, which are drying. We can have already the inoculation of the selective media on it. That's why these photos have different colors, so some of them are already with the added media. Sterilized, cutting, and the most important part is validation, to see if this actually would work as a microbial growth matrix. So just coming back again to the hydrogel deposition, to this base paper, like I said, we tried 3 different techniques. First one was drop casting. I mean, we have this paper in a base, in a mold. We just poured our hydrogel on top of it. Second is we kind of call a wet lamination. It's not really a wet lamination, but we have the reverse drop casting where the formulation is on the mold and we deposit the paper on top. Dry it a little bit and apply a little bit of pressure to make them stick together. And then the third method is a traditional bare coating method with a K-LOX proofer, for example. Each of these methods has some advantages and drawbacks, but we saw that when we tested the microbial growth of the samples, all of them worked quite okay. So in the end, what we have is this. We have a dry prototype, which has the dry hydrogel on the surface with the base paper below. And then after we add water, this hydrogel will absorb the water and we will have a similar consistency to the agar-based Petri dish. And then we can do our inoculation on this device and incubate it and see how this microorganism will grow. Here we have 3 possibilities. So for example, we can have just a dry blank without any media, and then we add the media, or the operator add the media that he really wants to test it. And our prototype will absorb it. After a couple of minutes, he can already start inoculation. Or we can already have our dry, preloaded prototype with media. So he just adds some water, and then it's ready for inoculation. And even for some specific cases, we can have our prototype with the media frozen. And after thawing, the operator can use this device for this inoculation. For example, this is a very specific case, and it is usually only for very sensitive media such as blood agar, which is all I know about blood agar, so please don't ask me more about it. And here we have just one slide showing the performance of this material against agar plates. So we have a series of diluted samples of E. coli samples. And I don't know, I think it shows, you can see well that there is a good correlation between microbial growth in the traditional agar plate and microbial growth in the PETRICELL dry prototypes. I mean, I just put one slide due to some time constraints, but we have been testing this almost weekly with our partners. So it always there is a follow-up of this. and not just regarding the microbial growth, but also the filling of the inoculation. Because the idea is to have something that can just be replacing this agar Petri dish. You're using the same methods, using the same equipment, and also that the operator has the same feeling while they are doing this. So the gel also has the same structure as the agar base. So with this, we have a cellulose-based growth media for this microbial analysis, which is ready to use in 50 minutes. It can be already preloaded with media or not. And since this is optimized to automatically replace the Petri plates, it already be, let's say, just plug and play in the traditional methods being used. Because it has a long shelf life, the way we tested, we have samples now reaching 9 months. So we say here 6, but it's already reached samples reaching 9 months. It has a long life, and this shelf life is at room temperature. So this lower a lot the requirements regarding temperature for stock and also the energy consumption. But we still have work to do, so we are still exploring different types of media which can be used. We also want to try to explore different markets because we see a potential for this in other applications. And also in the future, we hope to have this integrated paper-based Petri dish in order to even increase more the sustainability factor. Now we are also looking up at the scale-up process. So as you can see, formulation is quite different than a traditional paper coating. So sometimes we can have some challenges, but we are looking for partners for the scale-up. So if you also think that you or a company can help with this, we'll be happy to collaborate. And after all this, we have still the product certification. Now, quickly to the other project, which is GELA, which is included in one of the PRR agendas that we are part of. Basic GELA is a wrap to be placed around the container and helps this cool down this liquid inside faster. And its structure is like a double layer structure. So we have this traditional label paper or printable paper for brand placement. And then on the back, we have this cellulose-based hydrogel that will give the cooling down faster capacity. Again, for the hydrogel preparation, it's quite straightforward. We use this cellulose derivative, which can be hydroxyethyl cellulose, carboxymethyl cellulose, and so on, modified cellulose, which their function here is to uptake water and retain this water during the tests. It also can be added some different copolymers to improve the property of the hydrogel, crosslinkers, plasticizers, antifreeze, biocides, and so on. And let's show here. Yeah, here so we have two possibilities. We can have a more diluted hydrogel, or we can have a more viscous, more concentrated one, which we'll select based on the application methods. So, for example, for screen printing, we use the more concentrated one, or we also can use the diluted one for slot dye or bar coating. But for us, screen printing has been working quite well. So we mainly have been following up with screen printing. And now we have a video just showing how this technology would work. So we have different possibilities of how to start testing this. And conveniently, we started with beer. I think it was a kind of easy choice. So basically, you wrap this paper around the bottle, you wet it, you put it in the freezer, you wait for a couple of minutes, and then afterwards you remove it and it will be ready to drink. So it's very similar to what we can do with tissue paper around the bottle, but just the effect is kind of enhanced like this. And as you can see, in theory, it doesn't affect also the printing quality of the paper itself. And I guess our test subject will be quite happy. Yeah, there it is. I think you really like it. So we did the comparison with the traditional glass bottle, and we see that we can have a reduction of over 60% of the cooling time. And we use it, we even compare with the tissue paper cover bottle, and here we have like two discoveries. First, the tissue paper actually works. So this has been a discussion around some beer lovers. Yes, it does work. But with our prototype, with this kind of technology, we can go even faster. So we can cool down the beer in the freezer in 30 minutes. And this is based on the mechanism of controlled evaporative cooling. So The water which is absorbed there wants to evaporate, absorbs energy, and then cools down the liquid inside. Here is just a thermal image showing about this. So we see the bottle with the solution and without the solution. The temperature is lower, and also the temperature is better distributed around the whole bottle. And so with GELA, we have this fast cooling solution for beer bottles, not just for beer bottles. It's based on this evaporative cooling phenomena, and it's a cellulose-based material. It's simple to use. You just uptake water, put it in the fridge, and it's done. Reusable, recyclable, and biodegradable. And although we have this hydrogel layer, the hydrogel is not so thick, so it's very light and low-cost solution. And also, we can expect other types of containers, and this can bring to the brand owner some brand differentiation. So I reached the end of my talk. We talk about these two technologies, and I think that we achieved some of the target goals. For example, these are easy to implement solutions with improved or similar functional properties when compared to standard technologies, and we still have the added sustainability factor. So once again, I'd like to thank all my colleagues, all project partners, funding agencies, and all for your attention. Thank you.
Thank you, Bruno. Thank you very much for your nice presentation. So we move to Sandra Magina. She will talk about valuable polymeric products from lignosulphonates. Sandra is graduated in chemistry at the University of Aveiro and obtained her master's degree in material science and engineering in 2007. And her PhD degree in chemical engineer as well in 2021, also at the University of Aveiro. Currently, she is a researcher at CISECO, the Institute of Materials, the largest material science institute in Portugal. Her current scientific interests include the development of materials and polymeric formulations from technical lignins and valorization of agroforest residues and side streams from pulp and paper industry. The floor is yours, Sandra.
Thank you. Good morning, all. So I will talk about a project I developed during my PhD project. And the goal was to produce lignosulfonate-based products for 3 different applications: concrete, sensors, and adhesives. So very briefly, chemical industry produces dissolving pulp from eucalypt wood, and from the process there is the production of byproduct, a thin sulfate spent liquor, which is concentrated to get a thick sulfate spent liquor. Part of it is burned for energy production and recovery of the reagents, and another part is already processed and marketed for different industrial applications. Still, the valorization of lignosulfonates towards products with improved properties or even for new products is of great interest, and for these purposes, CAIBA provided me both thin and thick sulfate spent liquors from which I purified lignosulfonates, and I used them for the mentioned applications. So the first application was the production of lignosulfonate-based dispersants for concrete applications, and for this work, 2 strategies were used. So first, lignosulfonates are already used as plasticizers in concrete industry, and their dispersion mechanism is based on electrostatic repulsion forces. Lignosulfonates compete with the so-called super plasticizers. You have here 2 examples, polycarboxylates and ethylene-based polycondensates. Both of them are petroleum-based products. In the industry, they are used mixed with lignosulfonates because lignosulfonates are not enough to provide the dispersant efficiency required for the product. The dispersion mechanism of these products is also based on electrostatic repulsion forces, but in the case of polycarboxylates, it also combines steric hindrance. So the purpose of this work was to improve the dispersant properties of lignosulfonates to approach that of polycarboxylates. So 2 strategies were used, and the first one, and probably the most referred one in the literature, is the increase of molecular weight by modifying lignosulfonate using lacase to provide polymerization of lignosulfonates. The best condition provided a product with an 11-fold increase of the molecular weight, still soluble in water, and comparing the structure of this modified product and unmodified lignosulfonate, you'll see that there was a significant reduction of the number of methoxyl groups and significant change of the SG ratio of the product with the decrease of the S structures, most probably in the C5 position. Also, there was a decrease of the tertiary aromatic carbons along with the decrease of the number of hydroxyl groups, but also an increase of the quaternary and oxygenated aromatic carbons. And probably because the polymerization was via radical coupling by possible two mechanisms, the radical coupling of one electron oxidized lignin with another one, leading to the formation of aryl ether structure and biphenyl structures. So this was the first approach. The second approach to enhance the dispersant properties was the modification of lignosulfonates with epoxidized derivatives of polyethylene glycol and polypropylene glycol. So in the case lignosulfonates were modified with polypropylene glycol, there was a significant decrease of the number of hydroxyl group in G structures, which confirmed the modification, the grafting of polypropylene glycol chains in the lignosulfonate structures. These are the possible structures that could be present in the final product, but results suggest that the final product is composed of polypropylene glycol chains grafted in the lignosulfonate structure along with the polypropylene glycol homopolymer. In the case of the reaction, the modification of the lignosulfonates with polyethylene glycol derivative, it seems like no reaction occurred because there was no difference in the number of hydroxyl groups, and the results then suggest that the final product is made of unmodified lignosulfonates and polyethylene glycol homopolymer. So these modified products were then tested at SICA, and the fluidity of cement pastes were determined by measuring the spreading of these pastes. So superplasticizer were tested for comparison, and you can see that they gave the best results, especially the polycarboxylates. Lignosulfonates modified by lacase treatment gave results very similar to unmodified lignosulfonates, and this shows that increasing molecular weight without increasing the number of ionizable groups is not enough to enhance the dispersant properties of these products. And on the contrary, the polypropylene glycol derivatives or modified lignosulfonate show enhanced dispersant property, most probably because the dispersant mechanism combines electrostatic repulsion forces along with steric hindrance. So these are very promising results. I only want to show additional results related with the zeta potential values. For those who work with this subject, you'll find that in the literature, they state that zeta potential values are enough to determine the dispersant properties of this type of products. And as you can see by the results, all lignosulfonates, modified or unmodified, have similar results for zeta potential values, such as the naphthalene-based condensate, which is superplasticizers. And this shows that these values are not enough to assess the dispersant properties of this type of products. Now, this gave promising results, and now I will go on with the second application, which is the production of lignosulfonate-based conductive composites for sensor applications. So, as you know, the detection of transition metals in wastewaters and the environment is crucial because of environmental and health concerns, and this can be done by several methods, including potentiometric sensors. So in this case, the goal was to produce lignosulfonate-based polyurethane conductive composite, where lignosulfonates were used as the polyol, mixed with carbon nanofillers such as multi-wall carbon nanotubes to increase the electrical conductivity of the composite, and the isocyanate, which is kind of unusual, but it has a flexible chain to impart some flexibility to the final products. The most promising formulation was then used to produce the potentiometric sensors. So, different formulation changing the amount of carbon nanotubes were prepared, and as you can see from the electrical conductivity curve, it doesn't fit the percolation theory model, which is expected for this kind of products, most probably because there was some difficulties in the mixing lignosulfonates with the carbon nanotubes due to the presence of carbon nanotubes bundles and also aggregation of lignosulfonates. Also, you can see from the pictures of the membranes of the composite, there are some bubbles trapped within, and this also can cause disruption of the electrical conductivity path. Still, interesting results and good increase of electrical conductivity was obtained, and the most promising formulation chosen to produce the sensors was the one containing 1% carbon nanotubes in the formulation. So we prepared the sensors and we measured the sensitivity to different transition metals, and then as you can see at pH 7 this sensor is highly sensitive to several transition metals except for sodium and lead, and at pH 2 it exhibits also some sensitivity but also redox response to two ion pairs, iron and chromium. Although a high sensitivity, these sensors display some relatively low selectivity that should be improved towards chromium-6, except for cadmium and silver. So based on these very promising results, the possibility of producing sensors from lignosulfonates, other carbon nanofillers were tested, including graphene oxide, reduced graphene oxide, and also graphite. And as you can see, even increasing the amount of carbon nanofillers up to 10%, there was only a slight increase of electrical conductivity, so the type of carbon nanofillers to be used is really important, mostly because of the higher aspect ratio of the carbon nanotube rods, which are more favorable to the creation of a continuous electrical conductive network. So this was the second application, very promising results. And then I will go on with the third application, which is the preparation of lignosulfonate-based polyurethane adhesives. So polyurethanes are obtained mostly from the mixing of isocyanate and the polyol, both from petrochemical sources, and due to environmental and health concerns, one of the efforts has been done is to substitute these petrochemical-based polyols by bio-based polyols. So in this case, polyurethanes were used where lignosulfonates were the bio-based polyols, And the particularity of this formulation was to add a little bit of water to simulate the use of the thick sulfate spent liquor, that because the final goal would be to use the liquid instead of the purified lignosulfonate to reduce the costs related with lignosulfonate purification. So the basic formulation was this one, mixing the lignosulfonate with the isocyanate and a bit of water, but due to difficulties in mixing all the participants of the reaction, we study also the addition of polyethylene glycol with low molecular weight to overcome the limited accessibility of the hydroxyl groups in lignosulfonate, but also to promote a more efficient homogenization as well as to improve reticulation. So the adhesion strengths of these adhesives were measured and compared with the commercial white glue, and you can see that some of the results are quite similar, some of them obviously lower, but still these are very interesting results and possible applications of lignosulfonates. So, as conclusions, lignosulfonates can be used for other applications than the actual ones. Concerning lignosulfonate-based dispersants, the best approach that we got, the most promising strategy was the modification with derivatives of polypropylene glycol. Regarding sensors, this is a new application, but it's also quite interesting, and I have to say that comparing this work with previous work with different lignins, the type of lignin used for this application is determinant for the results, especially for the sensitivity, but obviously some work has to be done to improve selectivity. And regarding adhesives, well, this is also interesting and very promising, but of course a lot of work still has to be done. Thank you.
Thank you, Sandra, very much for your very nice presentation. And we will move to another presentation about cellulosic fibers, man-made cellulosic fibers from Eucalyptus globulus, a bridge to a sustainable future, with Daniela Ferreira. Daniela Ferreira has a PhD in chemistry in dissolution and homogeneous medium derivatization of cellulose. In the last 2 years, she has been working at CINTI, the Center for Nanotechnology and Smart Materials, producing cellulosic fibers through the wet spinning process.
So, good morning for everybody. I'm happy to be today here, and I would like to thank you for the commission, the organization of the conference, to have the opportunity to show you our efforts and results about the man-made cellulosic fibers. Here, our overview about what we will talk. I will talk a little bit about the CENTI, the institution where I work, some of the motivations, goals, our main results, and of course some final remarks. About CENTI, so we are a non-profit research institute that was founded in 2006. We are located at Vila Nova de Famalicão in the north of Portugal, close to Porto and Braga. So as a research institute, we are a multi-sectorial area, so we develop research, technological, and also engineering solutions for functional materials, smart materials, and also some engineering areas. As a multifunctional department, we have solutions for nanotechnology and smart materials, sustainable and bioeconomy, and also some digital and electronic devices. So for show you the motivation of our work, I would like to show you Portuguese TV news about our project. I apologize for the non-Portuguese speaker, as it is Portuguese TV, so all the interview it is in Portuguese. But after we will recover the ideas in English.
São uma alternativa às fibras importadas da Ásia, querem diminuir a dependência do mercado estrangeiro e acrescentar propriedades funcionais aos têxteis.
Projeto pioneiro em Portugal. O objetivo é tornar mais sustentável o processo de criação de fibras têxteis a partir de madeira de eucalipto.
Estamos a tentar desenvolver um processo alternativo, novo, é baseado num circuito fechado de solventes que permite fazer a dissolução e regeneração das fibras têxteis e, portanto, mais ambientalmente benigno.
Uma das mais antigas produtoras de celulose no país juntou-se a 2 centros de investigação de tecnologia têxtil para diminuir a importação de fibras.
O principal objetivo passa por tentarmos ter aqui uma produção local com um menor impacto a nível ambiental.
A Ásia faz estas fibras, mas importa da Europa as pastas. E depois estas fibras voltam à Europa para ser produzidos têxteis.
A origem das matérias-primas é cada vez mais importante a nível global. As empresas procuram soluções inovadoras para certificar os produtos.
Também estamos a tentar, com alguns aditivos, garantir que temos uma total rastreabilidade da nossa fibra de eucalipto, na sua origem, até ao produto final. E isso, sem dúvida, que se trata de uma inovação, diria, a nível mundial.
A investigação pretende também acrescentar propriedades funcionais às fibras para serem utilizadas em têxteis técnicos.
As fibras com acabamento antimicrobiano, retardência à chama, podem ser aplicadas à parte da indústria hospitalar, por exemplo, proteção pessoal, como por exemplo a parte de fatos de bombeiros, ou seja, há aqui um grande leque de aplicações.
O grupo empresarial ainda não tem data para estas fibras chegarem ao mercado. Assegura que serão viáveis a nível económico e também mais amigas do ambiente.
So, as we mentioned, and it was mentioned in the news, we want to fulfill a gap that there is in Portugal industry. So, as we could see yesterday during the technical visits, Portugal has a traditional and very well-known companies to produce pulp and paper. And also in the north of Portugal, mainly, we have a very strong textile and cloth industry that uses also the man-made cellulosic fibers that are artificial fibers. But we don't have here locally production of this kind of fibers. So we produce the pulps, send for a foreigner country, and then import back the fibers that we need to produce our textiles. So this consortium has the aim to boost the technology in Portugal in this area of man-made cellulosic fibers to make strong the industry, the local industry, and all the textile value chain. The consortium is formed by 2 research institutes, that is CENTI and CETEV, that have experience in fibers production and also the characterization and production of the textiles. Altri, through the Caimas mill, to produce the pulp and also the other products of cellulose, and more recently, University of Aveiro, that also has a lot of knowledge on the cellulose area. So our first project that started in 2021, it was the Fiber for Fiber, and we would like to optimize the eucalyptus globulus dissolving pulp produced by Caima to be conformed to produce the man-made cellulosic fibers. And we also would like to produce some functionalized fibers to the technical textile and also create a system to make the fiber traceable. And more recently, the Fiber for Fiber has finished last June, and the consortium will continue and we are working now at BEAT, that is Bioeconomy Act Textiles, that it is the Recover and Resilience Program of the European Union. It counts with 54 entities divided in 4 pillars. We are in the first one, that is biomaterials, and our main goal it is to produce the cellulosic fibers using local produced raw materials, and also empowering the local fabrics, and also making traceable and counterfeit fibers, environmental friendly process to make the fibers. So some of our developments until now, this is a resume of the process. So we have the pulp. It has to be dissolved in an appropriated solvent, and the solution is called dope. And the dope, it is spinning in a wet spinning process until we got the lyocell fibers. So the first step, it was the optimization of the cellulosic pulp. So the acid sulfide process of Kaima, it was optimized to get a dissolving wood pulp with the characteristics appropriate for the lyocell. So we have a low kappa number and brightness, showing that we have a high cellulose content, and also a short range of intrinsic viscosity that is optimum for the cellulose fibers production. After that, we started the dissolution of the cellulose. We did optimization of the parameters of the solution. We used the N-oxydenimethylmorpholinol as a solvent. It is a directed solution, so we don't need to derivatize the cellulose. And our main control, it is the temperature. We have to be careful about this because NMMO can degrade and also degrade the cellulose. So we take care of the heating bath temperature. We tried 120, 104, and 150, and monitor the temperature on the dope. So in the lowest temperature, it was not the best one. We have a low temperature on the dope. And the time to complete the dissolution, it was very long, to 450 minutes. And 140, we got the ideal temperature around 90 Celsius degrees. And the time it was in the range acceptable for the dissolution, 108 minutes. And with the 150 degrees, we saw that we go faster to the temperature that we would like. And after around 2 hours, we have to decrease the temperature of the bath to avoid the solvent degradation. And the control parameters of the dope, it is the water content that is measured by refractive index. And we saw that we are in the both conditions, in the 3 conditions, we were in the range that we would like, between 9 and 12. But looking at the microscope, optical microscope, we see that in the lowest temperature, we have a lot of cellulose fibers that was not dissolved. And in 140 and 150, it's okay, it was clearly dissolved. And we measured the zero shear viscosity of these dopes, and we saw that the lowest temperature, we have the lowest also zero shear viscosity because we didn't dissolve all the cellulose. And we also measured the dP of the precipitated cellulose, and it was similar to the initial one, showing that we do not degrade the cellulose. So based on these results, we choose the temperature of 140 to go to the spinning experiment. So to produce the fibers, we have designed a new pilot line that is able to work on viscose and lyocell process. This is it was a big challenge because this kind of machine is not on the market, so it was under demand. And here on the left, on the right side, we have the dope container and the spinning system, the pump, and the spinneret that is in the top of the first bath. After this first bath is the coagulation bath, and after we have the washing baths, dryer, and winder. For the lyocell process, we, as the dope needs to be heated during the spinning to lower the viscosity of the dope, we work in a configuration of dry jet wet spinning. That means that the spinneret is outside of the bath, creating an air gap of air on the top of the solution that where the fibers are created. And here on the left we have a picture of the spinneret with the fibers coming out before entering in the water. This spinneret has 100 holes with 100 microns on diameter, and the mainly control parameters were air gap distance and also the draw ratio, that is a ratio of the speed of the first godet and the extrusion speed. So we got our fibers, our first 100 Portuguese fibers that is made with pulp that is produced here in Portugal. It was dissolved here and also spinned here in Portugal. Okay. And we use a dope concentration of 10%, and we got fibers with the parameters good for the textile production, and it could be 19 in a jersey with 100% fibers of lyocell, proving that our fibers and the eucalyptus globulus dissolving pulp from chimas, it is suitable for the textile and clothing industry. After, as I said, we would like to have some functionalized fibers for technical textiles. Here are some preliminary results. So we would like to have antimicrobial fibers, flame-resistant, and luminescent fibers. So for the antimicrobial, we tried a biopolymer, and we had to make a modification on the physical size of this biopolymer to get a good compatibility with the dope and also the spinability into fibers. For the flame resistance, we use a clay, a commercial clay, and the best concentration, it was 10% based on cellulose. And for the luminescent properties, we also tried two pigments, one that is inorganic commercial pigment, that it was adequate, it was suitable for the spinning process and also the dissolution, and also a fluorescent polymer that is also commercial, but it was insoluble on the dope solution, and so we did not follow with that. To prove the presence of the additives in the fibers, in the case of antimicrobial fibers, we use a spectrometric method based on UV absorption. So we use the acid orange dye that have absorption interaction, preferential interaction with the biopolymer. So we can see when we use the modifier fibers, we can remove more dye from the solution, proving that the biopolymer is inside the fiber. The flame resistance also we used the thermogravimetric methods, where with the 10% of the additive, we could see the typical behavior with the lowering of the decomposition temperature and have increasing the residue. And for the fluorescent fibers, with the commercial pigment, here is an example with the phosphorescent pigment, and here is the white. At white light, we cannot see that there is something in the fibers, and under the light, we can see that it's emitting light, and here a video showing the phosphorescent effect. When we switch off the UV, it continues emitting light. So, some final remarks. We can say that the optimization of the process of CAIMA allowed to produce eucalyptus globulus pulp that is suitable for the production of man-made cellulosic fibers through the lyocell process. The lyocell fibers obtained, it is suitable for the textile and cloth industry, what allow us to have all the chain value here locally here in Portugal. And also our preliminary studies indicates that the functional fibers with the properties for technical application can be obtained by the incorporation of additives at the dope step. And we would like to stress that the partnership between industry, the companies, industries, and also the scientific technological entities is very relevant to develop and transfer technology and strengthen the national and local economy. So I would like to thank you for all the team that work on this project, and also for the financial entities, and thank you for your attention.
Thank you, Daniela. I'm sorry, I was a little bit rigorous with the time to save some time, some minutes for questions before the coffee break. So the discussion is open for comments, for questions.
Hello, Cristina Marques from RAIZ. Thank you very much for your presentation. It's very interesting to listen to all these new bioproducts showing up. I have the same question for Bruno and for Daniela, and that is if the price of these products is competitive with other options, with current options. I don't know if there's a market study or whatever. And I have another question for Sandra regarding, do we have any notion of when we will have a final product regarding the topics you mentioned? Thank you.
Okay, thank you for the question. Regarding the price, let's say starting from the first application, the PETRICELL dry, you don't have a final, let's say, result or final outcome of the price or the final price itself. We have some expectation based on the materials that we use and the process that we're using. But we think that due to the easiness of use, we think it will be competitive. Let's say we see some other alternatives in the market. I already talked about some, for example, the petrofilm, where you can just take your sample, put 1 ml, but we also already discussed with some participants here also about the limitations that this process has. And I think in having a dry media, and especially considering that you don't need to waste energy during storage, it will be price competitive, and also it will be easier to move these samples around. So you can send these samples to South America, to Africa, to Asia, to other places which may not have the same infrastructure as we have here. So I think this is a huge advantage. Regarding the second application, the price it will be slightly increased for sure, because we have the, let's say, a normal label, and then we have something else added. We also took in consideration this when we were trying to make or use our materials. So we try to make it as simple as possible, given the results that we want, that we expected. But in this case also, let's say, okay, we went for the beer, you can have a marketing push for this, but we can also go, let's say, for more noble applications. We can maybe think about helping cooling down blood faster, keeping urine samples fresh for longer. So I think also there is some work to on this regard.
Thank you for the question. About the fibers, the lyocell fibers is already on the market. Today it's a little bit more expensive than viscose one that is more it's the main man-made cellulosic fibers used in the market. But in comparing, of course, with the synthetic ones, it's much more expensive, but the quality of the lyocell is higher. And also now having more companies on the market, it is expected that the price goes down. And also the environmental process that is more sustainable can help to change to move on to these new fibers.
Thank you for your question. So regarding what I did during my PhD, regarding sensors, for instance, this was an alternative, and there's a lot of work to do. This is very promising, but of course these are very specific products, and for now it's in standby. Regarding adhesives, it was also preliminary results. There are lots of alternatives, and this is one that we decided to choose, but we could also work on isocyanate-free adhesives, for instance, so we only try to change the polyol, but for now this is very preliminary. There are so much routes to take that for now it's too soon to say anything about it. Regarding dispersion, so a lot of work has been done on this subject, and I did improve the dispersion properties of lignosulphonates, but the question is this a competitive product for the industry? Because in the concrete formulation, the industry mix lignosulphonates and polycarboxylates to reduce the costs, because polycarboxylates are really expensive. And the goal would be to improve the dispersion properties of lignosulphonates, to turn the concrete greener, if you can say that, to reduce the use of the polycarboxylate. So for now, the properties that we got are not enough to completely substitute the polycarboxylates. More tests are needed to check if the mixture that has to be used is enough to reduce significantly the quantity of carboxylates, and we did not do that. So we still don't know if these changes are enough for the concrete industry.
Thank you all. Any further question? Just a final one for Sandra. I think all of us are thinking about that. What about kraft lignin? You have been talking about lignosulphonates, okay, but do you think that it's possible to have the same applications from kraft lignin? Just comment briefly.
I believe that lignin is the future, honestly, but depending on the type of lignin, you will have different products with different performance. So you'll find in the literature lots of work, and kraft lignin, yes, it's the future because you have a lot big. For concrete, it will be probably more difficult because you need water-soluble products, so you have to make your kraft lignin soluble in water. So some work has been done on sulfonating lignin, but result is sulfonated kraft lignin. Does it display enough dispersion properties to substitute polycarboxylate? So probably you'll have to sulfonate lignins or turn lignin soluble in water and then make another modification. What does it do? It implies higher costs, and concrete is cheap. For sensors, you have a higher range for costs because it's functional materials, it has a higher price, you have a higher range to work with and to do some work. There has been some previous work done by Professor Dimitri with kraft lignin, and the performance of the sensors are completely different. So the type of lignin used is determined, but much work has to be done. Adhesives, well, you have some work with Nipus that you've done. So yes, it has potential, but different formulations and different results.
Okay, very nice. So let's thanks to all the speakers with a round of applause.